topic is nucleic acids. Well, nucleic acids are biomolecules. By now we know that molecules such as proteins, carbohydrates, including nucleic acids, are large molecules. Therefore, we refer to them as macromolecules. They are macromolecules that are found in the living organisms. So we refer to them as biomolecules. Okay, biomolecules. So how do we define nucleic acids? You did define proteins as polymers of amino acids. You also did define carbohydrates as polymers of monosaccharides. Okay, we can also define nucleic acids in that manner. Okay, so how do we define nucleic acids? Definition. Okay, so we can say nucleic acids are polymers. Nucleic acids are polymers of nucleotides. Okay, that is to say, the monomers are nucleotides. Okay, so the nucleic acids are built up by nucleotides. But before we proceed, it suffices to say that there are two types of nucleotides. Okay, types of nucleotides. There are two types of nucleotides depending on the sugar that is found in the nucleotide. Okay, some nucleotides are called ribonucleotides, meaning they have a ribose sugar. Another type is called deoxyribonucleotide. So these are the main nucleotides that you have. One is ribonucleotides, the other one is deoxyribonucleotide. So there are two types of nucleotides. So we can classify nucleic acids depending on the type, depending on the type of a nucleotide that is found in the nucleic acid. So, classification of nucleic acids. Okay. So we can classify nucleic acids based on the type of monomers it has. Okay. So if a nucleic acid is made up of ribonucleotide, that nucleic acid is called a ribonucleic acid. Okay. So we can say ribonucleic acids are nucleic acids that contain or that are built up from ribonucleotides. Okay. In short, ribonucleic acids, we call them as RNA. So RNA is just a type of nucleic acids that are built up by nucleotides called ribonucleotide. Okay. The other type is called the deoxyribonucleic acid. Deoxyribonucleic acid. Okay. So deoxyribonucleic acids are nucleic acids that are built up from deoxyribonucleic nucleotide. Okay? So we have distinguished the two main types of nucleic acids. Okay? There are two main types of nucleic acids. Ribonucleic acid, which is in short we say, or we abbreviate it as RNA. Then we also have deoxyribonucleic acid, which we abbreviate as DNA. Okay? Now it suffices to say that these nucleic acids have major functions in our bodies. Okay? We can say nucleic acids, okay? Nucleic acids store the genetic information. Okay? You are tall or you are short, you are dark or you are light, you have a deep voice or a small voice because of your genetic makeup. That genetic makeup is stored in nucleic acids. It could be DNA, it could be RNA. Some animals keep their genetic material in the RNA. But classically, DNA is the one that stores genetic information. Now if you look at my daughter resembles me. Okay? Why? Because my genetic makeup has been transferred into my daughter. So certain nucleic acid transfer this genetic information to the offspring. Okay? So we can say the other function of nucleic acid is actually to transfer the genetic material to the offspring. There are other functions that we will discuss as we proceed. But key, we have defined what nucleic acids are. We have then classified what we have classified them into two, DNA and RNA. Now before we go into the details, I think it will be good to sort of look at what makes up, okay? What makes up the nucleic acid. In other words, let's look at the monomers and build up to form the polymers. So we need to understand what are the polymers. Okay? What are the polymers? The polymers are nucleic acid, but what are the monomers? The monomers are nucleotides. Okay, so let's start looking at the nucleotides. We have said the nucleotides are monomers. Classically, nucleotides are monomers of nucleic acids, but they have other functions, which we shall look at later. But for now, nucleotides are monomers of nucleic acids. Now, these nucleotides are made up of three components. They are made up of a phosphate group. Okay? They are made up of a pentose sugar. And lastly, they are made up of nitrogenous bases. So the three are the components that make up nucleotides. What are nucleotides? These are monomers that build up nucleic acids. What are the nucleotides made up of? Phosphate, pentose, and nitrogenous base. So let's look at each of these components one by one. Okay, let's look at the phosphate. I'll skim through for the phosphate because we have already looked at it under buffers. So if you look at phosphoric acid, this is phosphoric acid. We did say that phosphoric acid can dissociate. When it dissociates, it produces a proton and dihydrogen phosphate. Dihydrogen phosphate. The dihydrogen phosphate can also decompose, producing a proton and producing hydrogen phosphate, which has a charge of -2. The hydrogen phosphate can decompose, producing hydrogen ion, can dissociate, and producing the phosphate ions, which are 3-. If you still remember, I gave you the pKa. We said the pKa1 is in the range of 2.4 somewhere there. Okay, the pKa2, we said it's around 7.15. Okay. Then we said the pKa, the pKa3 is around 12.4, somewhere there. These are approximate values. Okay. So the phosphate that you're going to find in our bodies will be in this form. Why? Because the physiological pH is in the range of 7.35 to 7.45. So at this value, at this pH, then it will dissociate to form this phosphate. So it will have a charge of -2. Okay, that's about it. The phosphate that you find associated with the nucleotide. Then thirdly, let's look at the pentose. Okay, pentose sugars means that it's a sugar, it's a monosaccharide that has 5 carbons. Okay, pentose are sugars that have 5 carbons. Now there are basically 2 sugars that you find in nucleic acids. Let me draw their structure. Okay, okay. Right, you may have hydroxide there, hydrogen there, hydroxide there, hydrogen there, hydroxide there, hydrogen there, hydrogen there, here CH2 and hydroxide. Okay, you can number the carbons. This is carbon number 1, carbon number 2, carbon number 3, carbon number 4, and carbon number 5. So there are 5 carbons, so it's a pentose sugar. Okay, it's a pentose sugar. Right, this is called D. Now look at it. This side, this CH2 hydroxide, we call it terminal hydroxide. Okay, this is terminal hydroxide. The one at carbon number 1, we call it anomeric hydroxide. Okay, so we have anomeric hydroxide and we have terminal hydroxide. So there's a terminal hydroxide at carbon number 5, there's an anomeric hydroxide at carbon number 1. Okay, so if you compare these two, where are they? Are they all pointing in the same direction? Yes, they are pointing in the same direction. Make a comparison with this one, the second one, the one I'm writing now. Okay. Okay. So what you see is that if you look at the terminal hydroxide and the anomeric hydroxide, they are pointing in opposite direction. Okay. So if the scenario is like this, we call this configuration as alpha configuration. If it's in this arrangement, we call it beta configuration. But we know that the sugars usually exist. This one I've written is a D. Okay, this is a D. Okay, this one is called D. Beta D ribose. This one is called alpha D ribose. Okay. Okay. The one that you commonly find in nucleic acid is a beta D ribose. All together, beta D ribose. Okay. The other one that you find is that, let me draw another one, another sugar, another pentose, which is in the beta arrangement or beta configuration. Okay. Now note, note, in chemistry, when you remove something, we say D. Okay, D. So when you remove hydrogen, we say dihydro. Okay, that means you have removed a hydrogen. If you remove oxygen, we say deoxy. It means you have removed the oxygen. So whenever you remove something, we say D. If you have removed sulfur, we would say desulfur. Okay. Now, this ribose has an oxygen here. Now I remove that oxygen. There is an oxygen here, but I have removed it so that instead of having oxygen, I have hydrogen. So it's the same beta D ribose, but it doesn't have oxygen. At which position? At position number 2. Remember, number 1, number 2, number 3, number 4, number 5. You always start naming from the anomeric. Always start from the anomeric hydroxide. So we'll call this as beta D deoxy. Sorry, we need to indicate the number where the oxygen has been moved to deoxy ribose. Okay, so these are the sugars that you will find, okay, in the nucleotide and in the nucleic acids. Okay, so we need to note the numbering system. Okay, we need to note where we are numbering from, always from the anomeric hydroxide or the anomeric carbon going towards the terminal carbon. Okay, now let's look at the third component. Okay, the third component of the nucleotide. The third component is the nitrogenous base. Okay, we are looking at them individually. So let's look at nitrogenous base. Okay, by definition, we can say nitrogenous bases are heterocyclic, planar, or almost planar, compounds with nitrogen as a heteroatom. Okay, heterocyclic, planar, or almost planar compounds with the nitrogen as an heteroatom. Now, there are two types. Okay, there are two types of nitrogenous bases. Okay, namely, you have the pyrimidines or pyrimidines and purines. Okay, pyrimidines and purines. Okay. Right. We can say that pyrimidines are six-membered heterocyclic. Let's not define it this way. Let me just say pyrimidines are six-membered nitrogenous bases to make it easier or shorter. Nitrogenous bases. Pyrimidines are six-membered nitrogenous bases with two nitrogen atoms. In the circle, if you want, in the ring, better say in the ring. Okay. Contrasted with the purines, we can say purines are nine-membered nitrogenous bases with four nitrogen atoms in the ring. Okay, So you see the difference. They are all nitrogenous bases. They are all heterocyclic, but we are saying that the pyrimidines are 6-membered. The nitrogenous base, the purines are 9-membered nitrogenous bases. Okay, so let's proceed and look at it. Let's proceed and look at each of these individually. We'll start with the simpler ones, the pyrimidines. Okay. So we will not define them. We have already defined them. Okay. But the pyrimidines are 6-membered nitrogenous bases. Okay. The basic structure. Okay. The basic structure of pyrimidine, I can draw it this way. Okay. They have a double bond. Okay. Right. Remember, nitrogen always has a lone pair there. Okay. This is called the pyrimidine. Okay. If someone is not following, let me draw it this way for the sake of someone who's not following. Okay. Okay. Whatever I'm doing, I wanted to write the carbons there. Okay, you have a double bond there, you have a double bond there, and you have a double bond there. Okay. Or if you want, if we are saying we are displaying the display formula, you have hydrogen there, and hydrogen there. Okay. Let's see a pyrimidine. This is the parent compound. This is non-substituted pyrimidine. But the pyrimidines that you find in nucleotides are substituted. Okay? They are substituted. Let's look at it. Substituted pyrimidines. Substituted pyrimidines. Okay? Okay. So, what I will do is that, fine, before we look at substitution, we need to number the carbons. Okay, we need to number the carbons and the nitrogen. So, we can start on any nitrogen for the non-substituted one. We can start on any nitrogen, but go towards the other nitrogen in such a way that the next nitrogen has the least possible number. For instance, if I start here, number 1, number 2, number 3, number 4, number 5, and number 6. Okay? The next nitrogen has 3. Okay? But if you started from here and say number 1, 2, 3, 4, 5, 6, the next nitrogen has 5. So which one has a lower value? The one in green. So we always go for the one which will give us the next nitrogen to have the least possible number. Okay, so that is the case. So remember here there is a hydrogen. There is a hydrogen there. So I remove this hydrogen. I replace it with a amino group. Okay, this is your amino group. Okay. I attach it there. Okay. And then here there is a hydrogen. Instead of having a hydrogen, I replace this hydrogen with an oxo. This is an oxo. Okay, this is called the oxo. So I introduce an oxo. Okay, so I've introduced an oxo there. Okay, are we together? I have replaced an amino group. I've replaced hydrogen by an amino group at position number 4. I've also replaced the hydrogen by an oxo group at carbon number 2. Now let's take stock of the ring. Remember, this is carbon, so carbon must have 4 bonds. So 1, 2, 3. Let me put a double bond here. So they are now 4. Nitrogen must have 3 bonds. 1, 2, 3. So it's already occupied, but remember it has a lone pair. Let me go to this carbon. This carbon must have 4 bonds. 1, 2, 3, 4. So it's already filled. So I leave it. Let me go to this nitrogen. Nitrogen has 2. 1, 2. It has a lone pair, of course. Can I put a double bond here? No, it can't agree because there's a double bond there already. Okay, so instead I put a hydrogen there. Okay, then if I put a hydrogen, I can't put a double bond here. I can put a double bond there. Okay, right. So let's give it a try in terms of naming. What have we done? What we have done is that at position number 4, we have put an amino group. Okay. Then at position number 2, we have put an oxo group. Okay. What is the parent name? Parent name is pyrimidine. So the name of this pyrimidine, which is substituted, is called the 4-amino 2-oxo pyrimidine. Okay. Note, I didn't start with 2-oxo 4-amino, because you know from organic chemistry, which you learned in first year, is that these substituents, you can consider these as substituents. These substituent groups are listed in the name, starting with the one that comes first in the alphabet. This is O and this is A. So A comes first. So that's why I've arranged them as 4-amino 2-oxo pyrimidine. Okay. Right. Maybe let me write it here if you're able to see. 4-amino 2-oxo pyrimidine. Okay. Right. This is the first one. I go to the second one. Okay? The second one, instead of replacing hydrogen with an amino group, I decide to replace it with an oxo group. Okay? I have a nitrogen there. Okay? And I have another nitrogen there. Then at position number 2, okay, remember this is 1, 2, 3, 4, 5, 6. At position number 2, I replace the hydrogen by or with an oxo group. Okay? Then I try to balance off. If you look at this nitrogen must have 3. Can I put a double bond here? It won't agree. There's already a double bond. So this carbon has 4 already. If I put a double bond, it will have 5, which is not possible. Can I put a double bond here? No. Because this carbon has 4 already. If I put a double bond, it will have 5. So I introduce a hydrogen there. Remember, it has a lone pair. Okay? Can I put a double bond here? No.